Okay, hello again. We're going to pick up where we left off in Chapter 3. This chapter again is fluid statics, and today what we're going to do is just cover one section, which is explain how instruments work that measure pressure. So barometers, piezometers, manometers, tube gauges, and so forth. So I'm going to just skip ahead through all of our discussion about pressure, hydraulic machines, and the hydrostatic equation, and I'm going to stop right here and make a note that we are going to use both the head form and the head form and the pressure form of the hydrostatic equation to understand how instruments work for measuring pressure. So here we are at the beginning. There's a number of different types of instruments, and the first type is a barometer. This is pretty easy to understand. A barometer is basically a fluid, a working fluid. In this case, it's mercury. It's a mercury barometer. And there is a vat of mercury in basically a tub or a dish, and there's a closed tube inside here. And basically the height of this tube is going to be related to the pressure that's being enacted on the surface of the mercury. So you can see atmospheric pressure is pushing down, and as that pressure pushes down in that liquid, the liquid goes up in the tube, and the height of the liquid is then going to be related to the pressure being imposed by the atmosphere onto the top of the liquid of the dish, the open dish. Now the additional, so if we apply basically the pressure form of the hydrostatic equation, we get that the height of the column here, gamma of the mercury times the height of the column, is the pressure in the tube plus any vapor pressure that might be captured in the top here. But typically the gas pressure is much smaller than the liquid pressure, and so we can neglect it. So in this case, the atmospheric pressure is merely related to the height of the column, H, times the gamma of the fluid. In this case, it's mercury. Now, I did also want to mention, the book also mentions a second type of barometer called an aneroid barometer. And I don't have any graphics for that, but basically it's a similar type of thing where we have a coil that's responsive to atmospheric pressure. They're used a lot in atmospheric measurements, and that coil, just when it flexes, basically more or less due to the atmospheric pressure, it turns a gauge. So I just thought I'd mention that as well, since the book mentions it. Here's a Borden type gauge. A Borden tube gauge, and this instrument works on the principle that this tube, this blue part here, is basically a tube or a spring that responds to pressure differences, and as the pressure changes, this thing kind of flexes in or out, and the shape of the ring basically flexes and turns a dial, this pointer here, which basically over here turns the dial depending on the pressure. And you can see that this thing can be screwed into some sort of pipe, and the pressure then measured. And these are pretty good. They're very cheap, but they tend to wear out. If the tube gets used excessively, its elasticity basically will wear out, and so they need to be replaced. You need to be careful to keep them calibrated. And obviously at zero pressure, when the thing is disconnected, you can easily calibrate the thing by setting the needle to be zero pressure. At least you can calibrate it to zero pressure easily. Now here's another instrument called a piezometer, which are quite important, and these are actually limited to low pressures, and they're hard to use with gases, but they're quite often used with liquids. You can see that this is just a tube that's basically tapped into a pipe that has some flow in it, and this flow generates pressure, or the fluid has a pressure in it. It might even be a pressurized pipe. And if you want to measure the pressure at the center of that fluid, you can put a pipe, basically a tap in here, a piezometer. And that pressure in that tube is going to be directly related to the gamma of the fluid, whatever it is, times the rise of the fluid from the center of the pipe to the top that you can measure here. And this pipe, this tube, will be out atmospheric pressure. So the nice thing about this is we can choose this to be at gauge pressure, which is at local atmospheric pressure, and that'll be at 0 gauge pressure. And we'll see in a minute that that's very handy to do. So this is a very simple thing. We get the measure of the pressure at the center of the pipe. So manometers are kind of a similar thing to the piezometers, except that there are very many different types of these, and they all work on the concept that that the pressure increases as the depth in the fluid increases, and the pressure decreases as depth decreases. So that should say decreases as well there. And so what we see is in the simple example of the U-tube manometer here is, and we'll do this example here in a minute. This is from an example in the book. We see that we have an open tube, open to the atmosphere, so that the pressure at point 1 here will be 0 gauge. And then as we go down into this fluid here, we can see that we've basically gone down. We have a piece of fluid here that where we go down, and so the pressure, we have a positive pressure due to that fluid. Basically, it's going to take some pressure in this pipe to push that fluid up in that. So that's a positive pressure. Then we come around from point 2 to point 3. There, since this is all the same fluid, we go down and back up the same distance. There's basically no pressure difference between points 2 and 3 because this is the same, basically, manometer liquid. And then we also see that the pressure in the pipe has, there's some liquid from the pipe in this tube as well. And this is going to cause a pressure decrease because we're going basically up to this point. So the pressure will decrease as you go up in altitude. So we'll look at this example here in a minute. We'll get a positive pressure here and a negative pressure here. The same is true for all these different lengths here. All you need to do is keep track of all these different positive and negative pressure decreases, and then you add them up, and we'll see that in a minute. And then also, this particular type of piezometer is for measuring differential pressure at 2 points along the tube, along a pipe. And instead of using the pressure form of the hydrostatic equation as we did in 1 and 2, we'll see in a minute that we use the head form for this, and we can use it very simply, very simple equation to get the differential pressure between points 1 and 2 in this picture. So they all really depend upon the manometer equations. And the first one here, we're going to use this equation for a manometer that has an open end. That is something that's open to the atmosphere. And the reason why this is a good thing to do is because we know what the pressure is at that end. We usually set it to 0 gauge pressure at P1, and then all we have to do is add up the pressures going down in the fluid and subtract off the pressures, basically the heights going up in the fluid, and then we get the resulting pressure. And I'll show you how to do that in a minute. And then that differential gauge is going to use this equation right here, and we'll give you 2 examples of that. So let's do this first example. Water at 10 degrees is the fluid in the pipe. That's this fluid and also this portion right here. And mercury is the manometer fluid here. This is mercury, and it's an open end. And we know that delta H is 60 centimeters and L is 180 centimeters or 1.8 meters. So what is the gauge pressure in the center of the pipe? Now this is actually, the book shows you in gory detail how to go from point 1 to point 2 to point 3 to point 4. But what I'm going to do is just give you a more simple example of just showing you how to do it using the manometer equation. So if we're interested in the pressure at point 4, remember that we can just kind of skip to having point 1 be the gauge pressure at the open end. So that is where this is the pressure at point 1 is 0 gauge, and we want to know the pressure at point 4. That's going to merely be the addition. We're going to add all the things going down, all the heights going down. That's going to be the manometer fluid or the mercury times that delta H, and we're going to subtract off the fluid of the water, basically. So this is what we get, and we just plug in. And this is 0 gauge, so that's just going to subtract right out. The gamma for mercury is 133,000 Newton meter cubed, and that's going to be multiplied by 60 centimeters, which is 0.6 meters. And this value came from table, what is it, A4, table A.4 in the book. And we're going to subtract off that upward rise in the fluid. We have to subtract this because this is fluid, basically a rise. We're going up. As we go around this tube from 0 around to this point, we have to, wherever we go down, the pressure is going to increase, and wherever we go up, the pressure is going to decrease. So we have to subtract off that decrease, and water is 9,800 Newton meter cubed, and that's times 1.8 meters. And notice the units are all going to come out to be in pascals, because this, let me get a red pen, this meter is going to cancel one of these and make that a 2. That's Newton per meter squared, which is a Pascal. Same for this. And the ultimate answer will actually be a gauge pressure, because we started out with a gauge pressure at the open end of the fluid. So this is P4. And if we do the math here, multiply 133,000 by 0.6, we get 79.8 kilopascals. And we subtract off 9,800 times 1.8 is going to be 17.7 kilopascals. And so P4 turns out to be 62.1 kilopascals gauge. And if you check the example, I think it's 3.6, you'll see in fact that this is the correct answer. And it's a very simple problem if you apply the manometer equation. Now the next example I want to do is this one here. It's a differential manometer. So we know right away that if we look at the manometer equations, we know right away that we want to use this equation. It's for measuring differential pressure. So we're going to use this equation initially here to get the head, the change in head, and then from that we can easily find the piezometric pressure. So we're trying to find both, we know that this water flowing in this pipe at 50 degrees F, and the deflection of the manometer fluid down here is 1 inch. So delta H is 1 inch. So basically we have a closed system where we've got some pressure here and actually some pressure here as well. They're both pushing in, but we can see that the manometer fluid is 1 inch here. So we will use the head equation, the head form, and what we get out of that is that basically the head, the head is going to be equal to the difference in those two heights, Z1 minus Z2. And that is going to be this delta H, that 1 inch, times the gamma of mercury over the gamma of water minus 1. That's the equation. And so H is going to be 1 inch, which is actually just 1/12 of a foot. We're doing this in traditional units, so it's 1 inch over 12 inches equals 1/12 of a foot. And again, from table A4, we get that in traditional units, that the gamma of mercury is 847 lbf, pound force per foot cubed, over 62.4 for water. And we actually know what this ratio is. We've calculated it before. It's a little over 13, but we'll write that down here in a minute. So what we get, note that these units cancel, and so this whole thing here is unitless. It's just numbers, and so our final units are going to be in feet. So H, which it should be because its head is in feet. So we get feet for units, and we get, let me just do this right now, 1/12 of a foot, and this turns out to be 13.6, this ratio 847 over 62.4 minus 1. So we can see that we're going to have an answer that's close to 1 because this is actually kind of close to 12. 13.6 minus 1 is 12.6. It's just going to be 1 times 12.6 divided by 12. So in fact, the answer turns out to be just a little over 1, 1.05, and that's feet. Now that's fine, but that's one thing that we wanted to know. This is the head. But we also want to calculate the piezometric pressure, and we get that by simply taking PZ is equal to the head times the gamma of the water, which is this. So we're basically determining what the head is of the water, the head change in the water, and the piezometric pressure in the water. So we have this. We know that this is 9,800. I'm sorry, we're going to do this in traditional units. 62.4 lbf foot cubed. And this is now not a gauge pressure. Notice that this system here is a closed system. There's we don't know that these aren't open to the atmosphere, but this system is clearly not. There's no free surface here open to the atmosphere, so this is not a gauge pressure. And what we get for the pressure, the piezometric pressure now, is if we do these units, we're going to cancel one, and we're going to have basically pounds per square foot here. Let me just write that this way, just to be clear. I want to make sure that people are getting this. This is a pound force over a foot squared, and the numbers turn out to be 65 and a half. But this unit here is equal to pounds per square foot, PSF, not gauge either. So the piezometric pressure is 65 and a half PSF. And then finally, so that's how you deal with manometers, and we will do some examples of these in class. We'll do more problems like these in class, so you get a little bit more chance to work with these, and obviously you'll be doing some of these in your homework too. They're not too bad though, as long as we stick to the hydrostatic equation. So the final type of measurement device is a pressure transducer, and there's not much to say about this other than the fact that it's a bit more of a fancy device where we have some sort of strain gauge in here that is open to the pressure, and it flexes and causes an electric current or some sort of electric signal that then gets recorded in some sort of digital amplifier or some sort of amplifier that has a digital reading. And so this is kind of a more modern type of gauge, and works on this principle. So we don't have any examples of this. Obviously, in order to understand this, we would need to know how the strain gauge works and responds to pressure, and how the diaphragm works, and then how all the amplification works as well. So uh, we're not going to do that. What we're sticking to primarily in this class are the fundamental equations here that relate manometers to the hydrostatic equation. So that brings us to a close at the end of section 3.3. And next time we will talk about predicting forces on plane surfaces.